We are continuing our discussion of power series, Taylor series, intervals of convergence, and applications. And today we're going to be focusing on geometric series and the patterns that we have with those. So let's consider this geometric series. Let's write the first several terms. If I start with n is equal to 0, I'm going to have 5x to the 0, x to the 0 is just 1, plus, when n is 1, we'll have 5x to the first, when n is 2, 5x squared, 5x cubed, etc., etc., etc. So this is geometric. To get to every next term, what do we do? What is r here? What is the common ratio? Well, to get to every next term, we're going to multiply by x, right? So this is geometric. With first term, 5, and common ratio, x. Yeah? When does a geometric series converge? Well, a geometric series converges when the absolute value of the common ratio is less than 1. That was our geometric series test, yeah? So in this one, in our series, this will converge when the absolute value of r, where r is x, is less than 1, which means x is between -1 and 1. That is the interval of convergence for this series. And we were able to do that very quickly without doing the ratio test, right? Without checking the boundaries. We don't have to check the boundaries if our series is geometric. Okay? So if this geometric series converges, what is its sum? If a geometric series converges, then its sum is the first term divided by 1 minus r. True? So that would be, our first term here was 5. R is x, so that would be 5 over 1 minus x. This is a function, true? That is telling us that this series, which we wrote the first several terms for, that is equal to 5 over 1 minus x if the series converges. So if x is between -1 and 1. Okay? This is extraordinarily amazing because we were able to find the series for this function. This is a function that could be like f of x. That is the series for f of x, and we get its interval of convergence without much hassle at all. Not at all. Okay? So if a function is in this form, if a function is in that form, where r is an expression involving x, we can immediately write the power series. And we can very quickly get the interval of convergence. We don't have to go through the whole Taylor series pattern. We can just immediately get the power series. Okay? Let's see how this works. Let's find the Maclaurin series for this function. Okay? So, the first thing I notice about this function is that it is in the form of a geometric sum formula. So it's in the form of first term divided by 1 minus r. That's the first thing that you want to notice. It's in that form. So I'm going to write that down. The form is a over 1 minus r, where a is our first term, and r here would be 2x. So the first term is 1, r is 2x. So on its interval of convergence, this series, this f of x, let me rewrite that for the sake of your notes. You wouldn't have to rewrite this, or you wouldn't have to rewrite it in an actual problem, but for the sake of your notes, this will equal, if it converges, it's equal to, our first term is 1. To get to our next term, we multiply by r. 1 times 2x is 2x. To get to our next term, we multiply by r. 2x times 2x is 4x squared. To get to our next term, we multiply by 2x, 8x cubed. And we could keep on going, keep on multiplying by 2x every time. Okay, what would be the general term for this? The general term would be, well, everything is positive, we would just have 2 to the n, because we're multiplying by 2, and then x to the, that's also increasing by 1 each time, 2 to the n, x to the n, and that would be our general term. For what values of x does this converge? We don't have to do the ratio test, not if it's geometric. I wouldn't do the ratio test if I know that the series is geometric. So this converges if the absolute value of r is less than 1, which means 2x is between -1 and 1, which means that x is between -1/2 and 1/2. That is the interval of convergence. No need to check the endpoints, because if the absolute value of r is equal to 1, I know that this will diverge. I don't have to go check it. So no endpoint check. Let's do another one. Number 2 here. Find a Maclaurin series for this one. So again, I notice that it's in the form of the geometric sum. It's in the form, it's close to a over 1 minus r, but it's not exact because I have a 4 there and not a 1. Very, very easy to get a 1 there though. So f of x is 1 over 4 plus x. How do I get a 1 in that spot? I just multiply top and bottom by a 4th. So I would get 1/4 divided by 1 plus 1/4 x. And now it is exactly in the form that I need it to be. My first term is 1/4, and my r is a negative 1/4 x. Make sure you bring out that negative. So the series will be on its interval of convergence. It will be, let me rewrite that. Okay, start with your first term, 1/4. And then to get to your next term, we're multiplying by negative 1/4 x. So it's going to make me alternate in sign. Negative 1 over, I'm going to make that 4 squared x. Now multiply by another negative 1/4 x plus 1 over 4 cubed x squared minus 1 over 4 to the 4th x cubed, etc. Keep on going. If they wanted the general term, what is the general term? So we are alternating in sign, starting positive. And then I just have a 1, and then x to the nth divided by 4, but I'm starting with a single 4, so n plus 1 there. Okay? For the interval of convergence, we know it's geometric. It converges when the absolute value of r is less than 1. The absolute value of negative 1/4 is just 1/4, right? So this is the absolute value of x divided by 4 is less than 1, and that means that the absolute value of x is less than 4, so x is between negative 4 and 4. Okay? Let's do another one. Let's find a power series for this one, centered at 0, and find the interval of convergence. So, again, I notice that the form is a over 1 minus r. The form is, but we have to do some work to get it to be exactly in that pattern. So I'm going to take my 4x over x squared minus 3. Okay, I'm going to multiply top and bottom. I want to get this thing to be a 1. Okay, I want it to be a positive 1 because it's a positive 1 here. So I'm going to multiply top and bottom by negative 1/3. And we will get negative 4/3 x divided by negative 1/3 x squared plus 1. Which, of course, we could rewrite as 1 minus 1/3 x squared in the bottom. Okay? Now it's exactly in that form. So the first term is negative 4/3 x, and r is positive 1/3 x squared. So my series will be, I start with my first term. To get to my next term, I multiply by 1/3 x squared. So I'm multiplying by positive, so it stays negative here. And we'll have 4 on top, 3 squared on the bottom, and 3 x's. The next term I multiply by 1/3 x squared, it'd be 4 on top, another 3 on the bottom, and 2 more x's. And we could keep on going if we wanted to. Minus dot dot dot, yeah. I guess we could write our general term, minus, if I put a minus there, it takes care of all the negatives. 4 on top, x to the powers are differing by 2, so 2n. I'm starting with a 1, so plus 1, divided by, I'm starting with a 3, so n plus 1 will do it. That would be me starting n at 0. There are other ways to write that, but that works. For the interval of convergence, we converge if the absolute value of r is less than 1. So this would be x squared over 3 is less than 1. So the absolute value of x squared is less than 3. Square root both sides. The absolute value of x is less than square root of 3. So x is between negative square root of 3 and square root of 3. Okay? Alrighty. Switching gears. We also need to be able to recognize versions of the Maclaurin series for sine, cosine, and e to the x. And, of course, the geometric pattern. We did that in Unit 11, so that's nothing new. when I'm asked to find this sum, I recognize these factorials on the bottom. I recognize those factorials as the factorials for e. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus on and on and on. Well, up here, I don't have x's, I have numbers. What must x be? X here must be 3. If x is 3, everything matches. So this is e to the third. Not e to the x, e to the third, because x is 3. For this one, I notice my factorials are odd factorials, so I'm focusing on sine x. Sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Okay, what must x be this time? Well, I see the negative x cubed over 3 factorial. Here's negative 8 over 3 factorial. X must be 2. Does it work for everything? It does. So this is sine of 2. Sine of 2. Let's do this one. I see all my even factorials, so I know I'm looking at cosine. Cosine of, or a version of cosine anyway. Cosine of x starts with 1. There's my 1. Then it alternates in sine. X squared over 2 factorial. X to the 4th over 4 factorial. Negative x to the 6th over 6 factorial. On and on and on. And again, I want to know what x is. X here must be pi. X must be pi. All the signs check out and everything. So x must be pi, so this is cosine of pi. We couldn't do anything with sine of 2, but I certainly know what cosine of pi is. That's just negative 1. As a multiple choice answer, that would be negative 1. Number 7. This is not a Maclaurin. Well, yeah, I could think of it as a Maclaurin, but it's not. There are no factorials down here. No factorials. So I'm not looking at sine, cosine, e. I'm not looking at those. I'm looking at a geometric sum. This is a geometric sum. So I know the formula for a geometric sum. It is the first term over 1 minus, the first term here is 1, over 1 minus r, whatever r is. We need to find out what r is. So what are we doing to get to every term? Well, r is definitely negative, because I'm multiplying by a negative. On top I'm multiplying by a 2, on the bottom I'm multiplying by a 3. And that works for every term. So r here is a negative 2/3. So 1 over 1 minus a negative 2/3. That would be a safe stop. Multiply top and bottom by 3 to get to our multiple choice answer. Alrighty? Switching gears yet again. Since we are writing functions as power series, we can easily differentiate or integrate the series using the power rule, either for derivatives or the power rule for integrals. This means that series are always differentiable and also continuous. Okay? In addition, so that's one big thing to know. These series are always differentiable and always continuous. Okay? In addition, the radius of convergence of the series obtained by differentiating or integrating a power series is always the same as that of the original power series. So if you know the radius of convergence of a series, you also know the radius of convergence for its derivative or its integral. You don't have to redo the whole thing. If you know that the interval of convergence for f is this, that has a radius of convergence of 3. And if the series for G is found by integrating or differentiating the series for F, then the radius of convergence for G must also be 3. It does not say that the interval is the same, because the interval for G might be different at the boundaries, but the radius will be the same.